Thank you very much for the nice introduction. I don't think I was ever introduced like that in a previous talk, so
there's always the first time.
Let me show my second screen. Yeah, you should all see my screen now. So it's a great pleasure to be here today and talk to you about learning the language of chemical reactions using transformer models. This is the outline of today's talk. I will start with presenting data representation models, which are super important for machine learning, and then tell you how the model I developed went into the IBM Reaction for Chemistry and RoboRXN platforms. In the third part, we will explore chemical reaction space together, and finally, I will show you why I think that those models work in chemistry. For any machine learning project, the data is really important, and the data I work with is chemical reaction data. That comes from the US patents, and I'm really grateful to Daniel Lau and also Roger Sale. Daniel text-mined the US patents in his PhD thesis at the University of Cambridge, and later also published an updated version in open source. And those datasets contain millions of chemical reactions, also represented as reaction smiles, as you see here. And if we take the 2D depiction, we have it like that. You see the two greater signs represent the arrows, and the dots, the separations between the molecules. When I mention atom mapping during my talk, what I mean is that every atom in the products, for example here, is mapped back to the corresponding atom in the precursors. But Daniel already warned us in his dataset description that while typically correct, the atom maps are wrong in many cases. And this was one of the motivations for me and my colleagues at IBM to mainly develop atom mapping independent models. For the next 40 minutes or so, this here will be the representation of choice, because it allows me to represent atoms as letters and molecules as words. And then after splitting those reaction smiles into so-called sequences of atoms separated by spaces here, I can borrow methods from human languages and apply them to chemistry. For example, I can cast the chemical reaction prediction task, where we try to predict the most likely product given the precursors, as a machine translation task. Machine translation in natural language processing is typically done with sequence-to-sequence model that, for example, translate a sequence in French, le chat noir, to a sequence in German, die Katze ist schwarz. And this is how such a sequence-to-sequence model looks like. On one side, we have an encoder that takes the different input tokens. So in our case, in chemical reactions, atoms, one by one, encodes them and computes the most interesting features from this sequence of atoms. And then on the other side, we have a decoder that, given this context vector here, produces atom by atom the product until it predicts an end token. And then we know that the molecule is complete. What was the problem with those early sequence-to-sequence architecture is the fixed-sized vector in the middle. Sometimes when the inputs were too complex, not all the information could be captured in this fixed-sized vector, and then the decoder would fail to predict the correct product. People, a researcher in natural language processing, came up with a solution which is called attention. Compared to the last slide, the encoder now encodes every single token, every single input individually, saves them in a memory bank, and then at decoding time, so prediction time, the decoder can query this memory bank for the most important features to predict the next token. So the attention mechanism gives the decoder the ability to focus on the important parts of the input. In 2017, Vaswani et al. From Google introduced the transformer architecture, which was fully based on stacks of attention layers. And they also introduced the multi-head attention that allowed the decoder, for example, to look at multiple tokens, multiple important parts in the input simultaneously. We adapted the transformer architecture to reaction prediction when I was in Cambridge, and without integrating any rules or chemical knowledge, this model could accurately predict chemical reactions and performed better than other approaches on the standard reaction prediction benchmark datasets. And really, it's a model that is trained just by seeing example of correct outputs and inputs, and just by repeatedly seeing those examples, maybe within 2 days, the model captures the important patterns, and given an unseen input, then it is able to come up with a product that, at least on the benchmark datasets that we have, is quite accurate. When I transitioned to the University of Bern, we asked the question, what is missing in those transformer reaction prediction models? And two things that were obvious were stereochemistry and experimental validation. And that's when I teamed up with Giorgio that you see here on the right, and we worked on this transfer learning approaches for predicting carbohydrates reactions. And Giorgio performed a 14 steps synthesis of a lipid-linked oligosaccharide in the lab. And on this test set, and also 2 other test sets, we could see a huge accuracy increases using the transfer learning approach for carbohydrates. This, for example, is one of the glycosylation reactions that was in the JAX test set. And while the atom mapping is kind of obvious to see, even for a human expert, it's challenging to say whether the molecules react in axial or equatorial side, or whether they form an alpha or beta bond. And our model was able to predict this reaction. What is nice is that this transfer learning allows us to have to specialize our models on a small subspace of chemical reaction space using only small specific data sets, and it can be applied to nearly any reaction subspace of interest. A recent interest that we've observed is enzymatic reactions, specifically for sustainable chemistry. And there, when we want to train a molecular transformer prediction model on enzymatic reactions, one of the big questions is how we want to represent the enzymes. Could take, for example, sequence of amino acids, but this might be too long compared to the substrate molecule. And here, let me just show you 2 different studies, one by David Kreuter from the Raman Group, where he decided to represent the enzymes the same way as humans described it in the scientific publications, and added this as an input to the molecular transformer to generate this enzymatic transformer. And concurrently, we have also the work by Daniel Probst from IBM Research, who went for EC numbers as a representation for the enzyme in the reaction. And both approaches work quite well. This just as a side note, David's paper recently even made the cover of Chemical Science, and I just want to tell you like the story behind this cover, because it's probably the first ever cover that was designed by VQ, GAN, and Clip model and using the Unreal Engine pack. So basically what we gave as an input to this generative model was just this phrase here, this prompt: enzymatic chemical reactions, screen chemistry, and advanced Unreal Engine. And this is what the model produced, and we adapted it a bit to make the cover. And the really nice thing here is that researchers in generative images realized that by adding Unreal Engine behind the text prompt, those models would generate images with much higher quality. And yeah, credits to Catherine Krausen for the notebook that she made available online. Yeah, now back to science and to like chemistry. We use the molecular transformer also for multi-step retrosynthesis. And there we basically trained two different models. One for the retrosynthetic steps, going from products to precursors, and another one to score the different paths. So we use the forward prediction model to give scores to the different suggestions by the retrosynthetic model. And by doing this iteratively, we could have multi-step retrosynthetic predictions. What is different in our approach to common literature approaches is that we predict not only the reactants, but also the reagents, catalysts, and solvents, what we call precursors prediction. If you compare to what is done in other studies currently. We mainly did this because we wanted to be fully atom mapping independent and let our model generate as much information as possible. One thing that is always a challenge when we work with chemical reactions are the errors in the data set. And here I just want to point you to Alessandra's amazing work where she developed a method where she could automatically clean chemical reaction data sets using forgetting events. So during the training of a reaction prediction model, she would look at how many times the training reactions would be like learned and forgotten and learned again. And depending on this amount of forgetting events, or if the reaction was never learned, she could then automatically filter huge data sets. At IBM Research, we like to make our chemistry AI models accessible to the world. And we do this through this IBM Reaction for Chemistry platform, which is free, and there's even an API access, so you can check it out. What you get there is a nice UI where chemists, even without any coding experience, can simply draw molecules in the sketcher frames and then run predictions and get back the predicted molecules and confidence scores and so on. There's even a button to give us feedback if you want to. We have also the retrosynthesis feature integrated in the IBM Reaction for Chemistry platform. There you go. It exists in an automatic mode where you automatically get a few suggested routes, but also in an interactive mode that might be even more interesting, because there it's some kind of interaction game between the chemist and the AI model, because the AI model generates suggestions and the expert chemist can use his or her knowledge to select what disconnection he or she prefers. Here is some feedback that we got back in 2019 from Alessandro, who recently joined the IBM Reaction team.
Hello, my name is Alessandro Giovanni from University of Basel, and today I want to show you how I use IBM Reaction for my everyday research. And I selected for you molecule to synthesize, and the program is giving me the retrosynthetic pathway, the most convenient retrosynthetic pathway. And for example, in the case of this ketone, the program is telling me how to prepare it with halogen metal exchange, and then addition of the lithiated species to the acid chloride, and then the protection of the ether with pyridinium chloride to deliver the product. But this is not just the only result. There are other outputs given by the program, and I will show you another one. In this case, they do the halogen metal exchange on another substrate, and then they perform the oxidation with manganese dioxide and deprotect. And in my opinion, everything makes sense, and this helped me and my colleagues to achieve the substrates, the synthesis of every substrate.
Now you might wonder what's next, and on the next few slides, I would like to point you to RoboRXN. Imagine you're a chemist at home, and you connect to the cloud where you get access to a synthesis planning tool, as I was describing on the last few slides. But not only that, you have another model that converts the single steps that you have in your synthesis route into a sequence of actions that you could then perform it in a lab, or alternatively could also be executed on a robot. And we have the prototype of such a robotic synthesis platform connected to the cloud at IBM Research in Zurich, and collaborators from all over the world, even from the US, already successfully synthesized molecules through the cloud. Here's just one example of a photoacid generator synthesis. What powers RoboRXN is also Alain Vaucher's smiles to action model that basically learned to convert any arbitrary reaction equation written as a reaction smiles to the sequence of actions that then can be performed by the robot. And at this point, I would like to point you to all the members of this RoboRXN team that worked super hard in the last years, led by Theodor Leiner. In the first part of my presentation, I've shown to you reaction transformer models that transform a sequence into a sequence, so encoder-decoder models. I've shown you reaction prediction, where we go from precursor molecules to the most likely product, but also retrosynthesis, multi-step retrosynthesis, and even the smiles to action models that goes from reaction smiles to a sequence of actions uses those encoder-decoder transforms. In the second part of my presentation, what I will show you are encoder-only transformers that convert a sequence, in our case a chemical reaction, into a single value or label. And we use those to do reaction classification and yield prediction. But let me first zoom into such a reaction transformer. So the transform model is made of stacks of self-intention layers, and what it gets as an input are those tokenized reaction smiles, so a sequence of those single atomic tokens from the chemical reaction. Every self-attention layer in this block here has multiple attention heads that can learn different functions to attend the neighboring or all the tokens in the chemical reaction and learn better and better contextual representation. Why is context important? Let me make an analogy with human language. If you think of the word bank, then it has a completely different meaning whether you speak about the river bank or the bank where you get money from. And this really depends on the context of the word. And similarly, if we look at this chemical reaction here, a nitrogen or oxygen atom will have a complete different meaning depending on its nearest neighbors, on the atoms in the same molecule, but also the complete chemical reaction. And once we have this base that it's trained, we can put on top a regression head to solve a regression task or a classification head. So one layer to classification. The training of such a transformer model typically happens in two stages. First, a pre-training stage to put it somewhere in a favorable state, and then a second fine-tuning stage where it learns the actual downstream task. The pre-training we use is typically mask language modeling. It's basically a reaction corruption task where we mask different tokens in the input reaction, and the task of the model is to predict the masked tokens. And we can do this randomly for all the different chemical reactions that we have in our data set. And this forces the model to learn not only the Smythe's grammar, but also chemistry, because you cannot replace any atom with any other atom. Then we can train it on a specific task, like reaction classification. In reaction classification, what we use is data from Nextmove software, from the Pistachio database, and we try to predict the corresponding reaction class, so name reactions, given the reaction Smythe as an input. And on their data, we could be bit more, be more or less 98% accurate. But what I find even more interesting in this project that was published in Nature Machine Intelligence is that when we take away the last layer and only use the encoder part of the transformer model, then the outputs that we get are something like data-driven reaction fingerprints that encode all important properties of the chemical reactions. And using those data-driven reaction fingerprints, we could generate almost perfectly clustered chemical reaction space maps. This chemical reaction atlas is also based on the work by Daniel Probst that wrote this T-map algorithm to do this dimensionality reduction and generate those tree-like maps. Here you see a reaction atlas in action. It's interactive. We can display categorical or continuous variable. It gives you a feeling, an immediate feeling of the local but also global properties of your reaction data set. We can zoom in, we can highlight different chemical reactions, compare nearest neighbors, display additional information. It basically gives you a new way to explore chemical reaction space if you're interested, and we have tutorials available. Yeah. We can use this reaction fingerprint also to search for similar reactions. For example, if we gave this Mitsunobu reaction here as an input, those would be the nearest neighbors in our data set. And what you see is that it not only captured the transformation, the reaction center, but it's also suggesting reactions with similar reagents. So, and from that, you can then get back to more information essentially the pattern or the procedure that made the other reactions. We have open source code available, so after installing RDKit, you can basically pip install Reactionmapper, and it only takes a few lines of code to generate fingerprints. And recently, folks at AstraZeneca even wrote a reusability report on our package, and basically made it work on their own internal data. So we're super happy about that. Thanks a lot. Another downstream application that I will show you today is the prediction of reaction yields, more specifically of high throughput experimentation reactions. And this particular paper here by the Doyle group, where they predicted the yields of Buchwald-Hardwick reactions. It's one of the best studied reaction yield prediction benchmark dataset, I would say. And also last year, there's the Glorious group that suggested to concatenate multiple fingerprint features and also use a random forest model to predict those yields. What the Doyle group has done is they had computed physics-based descriptors using DFT and tested different models, but then in the end selected the random forest model as the best performing one. And those were the results that existed. And the question that we ask in this whole scheme of learning the language of chemical reaction is, how much information is available in the reaction smiles only? So what we did is to train reaction transformer on the task of like input reaction smiles and showing it examples of the corresponding yields and hoping that it would learn what is important for the yield. And we were positively surprised. Our reaction models really performed a lot better than previous approaches. The question then was, yeah, we all know that transformers, neural network, deep learning models are very data hungry. So how would it perform with less data? And even there, we were super happy to see that when we applied data augmentation, so basically used multiple versions of the same data points as in the training set, we could achieve even with less than 100 data points, training data points, results comparable to the ones that were done with physics-based descriptors. So yeah, it's super nice to have those huge models working even in the low data regime. So the obvious question then is, why do those transformers work so well in chemistry? And that's when I teamed up with Ben Hoover and Henrik Strohwald that you see here on the right. They're both visualization experts at IBM Research in Cambridge and also in the MIT lab. And what we did, the project setup, was to take millions of unlabeled smiles. There were ones from Daniel Lau that we could find in open source, train a reaction encoder, a reaction transformer on those smiles, just using this mask language modeling task, and then visually inspect what the model had learned. And we can really, Ben and Henrik built this framework to like go into the model and select a specific hidden layer. Here you have, okay, here you have to see that this model that we analyze has different heads and 12 layers. And then we can go and take a chemical reaction as an input and visualize what is important for a specific layer and head combination. And we do this by displaying the attention weights. So this might be a bit confusing in the beginning, but what you see here is the input smiles on top and also the input smiles on the bottom. And we split it in two so we could display what is important for a specific head to look at to learn a better representation of a specific atom. So in this case, something like the nearest neighbor. And doing that, we can go through different heads and layer combination and explore the model. And we did this, and we were like really curious to see what we would get. And at some point, we found layers like the following here. If you look closely, you realize that most of the precursor atoms somewhat point to the product atoms, and most of the product atoms point to the precursor atom. And if you remember the start of my presentation, then atom mapping should already be a thing for you. Indeed, we had the exciting thing here is that subparts of those transformer model automatically learned atom mapping without being told to do so. So in an unsupervised way, and we use this signal to build Reactionmapper. Reactionmapper is, as the name tells you, an atom mapping algorithm, and basically what you would get from a non-atom mapped reaction, it would produce the correspondence between the atoms in the products and the precursor, and give you, tell you how the atoms reconfigured. And the algorithm goes the following, is that we get the attention weights from the model, from this specific head that we selected. We iterate through the product atoms, map the most likely pair, which could be number 3 here to number 3 here, and then would increase the attention from neighboring atoms in the products to neighboring atoms in the reactants, as we know that they are likely to be also neighbors. So here I already show you the full atom mapping, but we would start from a non-atom mapped reaction, and the atoms would be tagged one by one. And using pure attention, we would already get like roughly 96% correct maps. And with this neighbor multiplier on top, we got up to 99% on a test set of high quality atom maps by Nadine Schneider and co-workers. Reactionmapper does not only produce high-quality atom maps, but it's also really fast. On a GPU, we map at roughly 7 milliseconds per reaction. And once we have a huge data set mapped, we can then start extracting reaction centers, bond changes, graph edits, basically the whole grammar of chemical reactions. And this can then be used to improve synthesis planning tools, potentially make quantum mechanical simulations more feasible, and overall improve the reaction accessibility and interpretability. On the next slide, I will just go into how atom mapping is used in synthesis planning. So we all know those great template-based approaches. For example, Marvin Segler's Nature paper used templates for predicting the reactions. Then we have graph neural network-based approaches that, given the precursors, predict which bonds are changing during a reaction. And as I've shown you in the beginning, we have those sequence-to-sequence, smiles-to-smiles approaches, like the ones that we developed at IBM. If we look at the two upper approaches, then they are both atom mapping dependent. Template-based approaches require atom mapped training data to extract the templates. Graph-based approaches require atom map training data to define the graph edits that they are then trained on. And On the other hand, our models, our smice-to-smice models, can be completely atom mapping independent, but we lose this tracking of how the atoms reconfigure during reactions. And this would be really nice to know, because we can get a lot more information on our predictions if we have this. So I would say all of those methods in the end benefit from having better atom maps. If you want to try out Reactionmapper, we have a demo online on Reactionmapper.AI, where you can simply paste in your smiles and look at the mapped reaction. But not only that, you can also explore other heads if you're interested to, and explore the internals of the model. And recently, there was a benchmark paper by the Warner Group, and Reactionmapper was actually selected as the best atom mapping tool, even better than some of the commercially available tools. Also for Reactionmapper, we have open source code available. So again, after installing RDKit, you should be able to do pip install Reactionmapper and have it running. We're super happy that it was in the end published in Science Advances and also highlighted in one of the CNN weekly newsletters. So that's super cool. And I'm already at the end of my presentation, so let me give you a short summary. In the first part, what you have seen are encoder, decoder, transformer models that we've used for reaction prediction, even for challenging reactions as carbohydrates with small data sets, and also for synthesis planning, the prediction of experimental procedures, and finally also to do automatic noise reduction. In the second part, we've used encoder-only transformer models for reaction classification fingerprints, building those huge reaction atlases, and the yield prediction in Buchwald-Harnweg reactions. Finally, I've shown you those models for atom mapping. This is just a last side note. If we think of language models, I don't know if you followed the trend in NLP, then you have every company just publish bigger and bigger models, more and more data. And I think this is not even the most recent slide, so it would be probably 10 times higher now. And the funny fact is that from the reaction prediction models, we started with 20 million parameters. This would not even be on this scale here. And we went down to 6.6 million with the reaction classification models. And in the end, the last model I've shown you has less than 1 million parameters. So we go the other way around, but still we are able to predict kind of nice things with those models. And yeah, if there's one take-home message, I guess it's that we have to be open to different representations, and that sometimes if we don't take the most obvious representation, we can get some inputs from other fields, like from natural language processing, and apply new methods to the chemical domain. We have IBM RXN for chemistry, a free platform where there's almost everything there, like reaction prediction, synthesis planning. You can even convert paragraphs, synthesis paragraphs, to structured actions, which could be useful too. And also, we have a RoboRXN simulator. If you want more details, ping me at some point, and I can point you to the right things. We've introduced those reaction fingerprints, and with tutorials for them if you want to build your own reaction atlas for your reaction dataset and start exploring reaction space like that. One thing that at least for me, was like the most surprising result of my PhD, is that we were really able to uncover those atom mapping patterns in the transformer models, and completely learned unsupervised. So without the model having seen atom mapping at any point of the training, and this somehow, this means that this pattern must be there somewhere in huge chemical reaction data sets, and I find this super interesting. And using this signal, we could develop Reactionmapper. At this point, I would like to thank all my amazing collaborators, because without them, none of this would have been possible in the last few years. Let me just highlight Theodore Leiner, who is my supervisor at IBM, and Jean-Louis Levenger, my PhD supervisor at the University of Bern. Maybe just the last point, Alexander mentioned that I'll be starting at EPFL next year. So if you know excellent PhD candidates or better master students that would like to do a PhD, potentially in Switzerland, on machine learning for chemistry somewhere at the intersection, then please let them know. I'm looking for great candidates. And thank you very much for your attention.